In this video, we will discuss the silver quant silver leverage model. We will discuss how the model is derived and how it is interpreted. We will also talk about how the model is fit to mining data, and we will talk about which values can be derived from it. First, let's discuss the meaning of leverage. Leverage refers to the capability of amplifying gains and losses. Typically, leverage is achieved by taking on debt, such as in the case of margin debt when purchasing stocks, or mortgage debt, or purchasing futures on margin. Leverage can also be achieved with options, but for the case of precious metals miners, they achieve leverage to the metal price in a different way. The first key idea in this video is going to be that miners have leverage because they have costs. And we are going to see that through these math formulas here. So the first formula states that a miner's profit is equal to the metal price that it receives minus the costs incurred in extracting that metal. Now for Formula 2, we are going to discuss what new profit level a miner will enjoy upon a percentage change of the metal price. Okay, so the formula states that the new metal price is given by the old metal price times the percentage change plus 1 minus the cost. Here we are assuming that the cost is unchanged. Now the metal relative variable, or percentage change of the metal, might be a value like 0.01 for 1%. Okay, that's why the 1 must be added to it. Okay, now on Formula 3, we are talking about the percentage profit change, and its formula is given by the new profit level divided by the old profit level minus 1. We can plug Formula 2 into Formula 3, and we get Formula 4, which in turn may be simplified into Formula 5. Now the green portion of Formula 5 is a quantity that we are going to name. We're going to call that the leverage, which gives us Formula 6. Now Formula 6 is telling us that the percentage change of the profit is equal to the percentage change of the metal times some number, the leverage factor. Now that leverage factor, or the green highlighted portion of the expression, is, let's take a closer look. It is the metal price divided by the difference of the metal price and the extraction cost. Now right away we could see that if cost is 0, leverage becomes 1. In other words, zero cost miners have no leverage. If the cost is, for example, half the metal price, then the green expression evaluates to a 2. Okay. Now a miner that has leverage 2 will experience a 2% profit increase for a 1% metal price increase. What we are interested in doing next is deriving a new formula from the one we just derived. So the new formula that we are seeking will be one that relates the metal price to the share price. Now that's not the same as relating the change of metal price to the change of profit level. Okay, now here we are also going to assume that the stock price is proportional to the profit level. Okay, so we're basically going to replace profit with stock price. Okay, now using calculus notation, we have the formula at the bottom, which is saying that the percent change of the stock is equal to the percent change of the metal times some constant leverage factor K. You could think of the DS calculus notation as meaning delta S or small change in S. Okay, so that's how you write it in calculus. Okay, so let's proceed with that formula. We are going to integrate both sides to get the second formula, which states that the log of the share price is equal to the leverage factor times the log of the metal price plus C. Okay, now remember this formula. We're going to use this intermediate result later. Now, proceeding along, we can exponentiate both sides and then simplify to get the final formula at the bottom, which is stating that the share price is equal to some constant times the metal price raised to the kth power. Okay. Now, formulas of that nature are called power laws. And so we could say that the price change formula that we started with implies that the price levels obey a power law. Okay, now that formula that I ask you to remember states that the log of the share price is equal to the log of the metal price times some leverage factor plus some constant. Okay, formulas of this shape are linear, or they form a line. It's the familiar y equals a times x plus b format. Okay, and so what this is saying is that if we take the log of the share price, and we're going to use that for our y variable, and we're going to use the log of the metal price as our x variable, if we plot that data, then according to this model, we should get a straight line. Here's Hecla. We have 1 dot per day. On the x-axis, we have the logarithm of the silver price, and on the y-axis, we have the logarithm of the share price. You can see the cloud of points trends upwards, and you can see that, it sort of forms a fat line, I guess I might say. On the right-hand side, what we've done is connect consecutive dates with straight lines. So this shows you how chronologically the prices have evolved. The X and Y positions are identical on both the left and right charts. The only difference is we're drawing line segments instead of unconnected dots. Now, the important concept here is that we would like to fit our model to these data. So our assumption is that these data form a straight line, and we want to calculate the settings of the model that best capture these dots. Okay. Now the way we do that, the way we fit a straight line to dots, is using the least squares algorithm. Okay. The output of that algorithm will be our slope, which is the same as our leverage factor, and also the other constant, c, which is the intercept. Now, the leverage factor that we calculated is 1.6. All right, so there's a important result for Hecla. The past 2 years of data, Hecla has exhibited a silver leverage of 1.6. That's very interesting to know. Now, the other output, the C constant, also known as the intercept, is less interesting. You could think of it as a scaling factor, which handles the reality that, large caps might trade at multi-dollar prices, whereas we have other stocks which trade in the pennies range. So the intercept here is something that adapts the model to these different ranges and scales of the data. But for our purposes, we're not really interested in its value so much, and sometimes statisticians call those nuisance parameters. It's negative 3.2 in this particular case. Okay, so we have the slope and intercept of the line calculated using least squares. We can draw that line and overlay it on our dots. Now, what we really are hoping for is a line which lies very close to the dots. Okay, the closer the line is to the dots, the better we say the model is fitting. Okay. Now, that goodness of fit idea is quantified by the so-called R-squared statistic. And the R-squared statistic tells us how much of the variation of the dots is captured by our straight line. Okay. One way to think of it is that all these dots have a total variance from top to bottom of the chart, 1.2 up to 2. Okay, so they have a total standard deviation of 0.164. Okay. On the other hand, once we know that straight line, well, we could consider the distance from each dot to that straight line. Okay, now that's a much lower variance, much lower standard deviation on those quantities. That's called the residual standard deviation. Okay, so when we consider the fraction of the total variance that is reduced by the straight line, well, that's how we calculate our R-squared value. And in this case, we have a value of 0.84, which is pretty good. All right, now up until now, we have been making these charts on log paper. So we've been plotting the log of the metal price versus the log of the share price. Well, let's repeat the process without taking the logs. We're going to get a cloud of points that doesn't look so much like a straight line anymore. Okay, there's going to be some curvature to it. And in fact, that curve is going to be fit by the power law, which we derived earlier. Okay, so really the way to think about this plot is that it's that same cloud of points and it's the same straight line. However, we have no longer taken the logarithm of the x and y axis, so that straight line becomes a curve. This happens to be the chart that is displayed on SilverQuant. One characteristic of this procedure of looking at it without taking the log is that the error tends to increase with increasing price, okay? Because we've minimized percentage error, while the absolute amount of error will be an increasing value. So the spread around the line on the left side tends to be tighter than the spread around the line on the right side. And that's okay. That's what we want. So in summary, what we can say about Hecla using the silver leverage model is that the model fits the data pretty well with an R-squared of 0.84 and a leverage factor of 1.6.